part 3 of chapter 11, talking about simple harmonic motion. This section is going to concentrate on sample problem D, which is wave speed equation, but also different properties of waves. So the first question that I have for you is, if you were standing like on top of a cliff and you kick a rock or you drop a rock down into a lake below, what do you see when that rock hits the water? Like, what does the water look like? Well, waves will appear in circular patterns that move outward from the disturbance. So you would start here, and this wave would occur, then this wave would occur, then this wave would occur, then this wave would occur, etc., etc. So what I'm trying to get here is that it's not that you're seeing the water moving, right? Because if you would see the water move, wouldn't it be like a parting of the sea kind of an effect? Because the rock would fall and the water would move with the disturbance being the waves, right? Okay, so that's clearly not what's going to occur here. So it's that the disturbance, the particles are moving through the medium in this scenario in which the medium is the water. So we're going to talk more about that throughout this section here. So once again, a medium. By definition, a medium is a physical environment through which a disturbance can travel. Physical environment through which a disturbance can travel. Does the medium travel with the waves? So in other words, you drop that rock down into the water. Does the water move with the waves, or do the waves move through the water? Well, the waves move through the water. So no, the medium does not travel with the waves. So what is occurring? The waves, the disturbance, are moving through the medium. So I'm just going to put disturbance moves through the medium. An example is sound waves through air or ripples through the water. So here's a first example, here's a second example. So the idea of you guys hearing right now is because with your speakers on, there is air for the sound waves to travel through. If it was in a vacuum, your sound waves wouldn't have any medium to travel through, therefore you would not hear any sounds in your head. Okay, so the two mediums that we're talking about with sound waves and air waves, for lack of a better term, are air and water. So those would be called media, the plural of medium. Alright, so mechanical waves. Definition, mechanical waves are waves that require a medium to travel through. These are waves that require a medium to travel through. So for example, what we were just talking about is sound waves. So sound waves would be an example of a mechanical wave because they do require a medium. We're not going to get too far into sound waves because that's honestly what chapter 12 is entirely about, but just to put that idea in your head. So my question for you, do all waves require a medium in order to travel? No. A really good example of that is the electromagnetic spectrum, EMS waves. Guys, what are some examples of EMS waves? Some examples of the electromagnetic spectrum. Well, some of them are radio waves. You have infrared rays. You have UV, ultraviolet. You have visible. You have gamma, etc., etc., and microwaves to get them all listed there, but there's just some ideas. So check out this little blurb here. This little blurb here says, the sound produced by the bell cannot be heard, since sound cannot travel through a vacuum. If there's vacuum, that means that there's no air molecules in that container there, that bell jar is technically what it's called. Therefore, you cannot hear that bell ringing. We can actually show this to you. Mr. Dillick and myself can show that to you. It's pretty weird. You hear the bell and then you don't hear the bell, but the thing's still moving. Okay, wave types. First type of wave we want to talk about is a pulse wave. A pulse wave is a wave that consists of a single traveling pulse. Wave that consists of a single traveling pulse. A periodic wave is continued generations of the pulses. So over and over and over and over and over again. So like a slinky going up and down, up and down, up and down, from the left hand to the right hand, from the right hand to the left hand, from the left hand to the right hand, from the right hand to the left hand. That would be periodic waves. So continued generation of pulses. So in other words, repeated path. A sine wave. This is periodic wave whose source vibrates with simple harmonic motion. See how they're building off of each other? Periodic wave whose source vibrates with simple harmonic motion. And then a transverse wave is a wave whose particles vibrate this is the important word right here. Oops. Perpendicular. To the direction the wave is traveling. Okay, next thing, a wave form. Displacements of a single particle as time passes. You're looking at the displacement of each point of the wave as a single moment in time. That's the key thing that I want you to know about a waveform. So what's the variable? What position would you be talking about on the x-axis if you were to graph a waveform? Your x-axis is going to be time. Okay, so your answer here is time, usually measured in seconds because of period, right? Period is s, frequency is 1 over s, so that should make sense. Okay, wave measurements. The first one we want to talk about is a crest. Crest is the highest point above equilibrium position. Highest point above equilibrium position. Whereas a trough is the lowest point below equilibrium position. Wavelength, kind of longer one here, guys. Distance between two adjacent, similar points on a wave. Distance between two adjacent, yet similar, points of a wave. In other words, crest to crest, or trough to trough. Amplitude, height of a wave from equilibrium position. We're going to move this over here, and I'm going to use a different color. We're going to call this a crest. Actually, we're going to draw in our equilibrium be what a wavelength is looking like. By the way, wavelength is lambda. It's an upside down Y. The letter lambda is wavelength. Okay, next here is longitudinal waves. Longitudinal waves are a wave whose particles vibrate parallel to the direction of travel. Areas of compression, you're talking about a crest on a sine wave. When you have high density and high pressure on a longitudinal wave, then you're looking at a crest. Areas where you're stretching this wave apart are going to be similar to a trough on a sine wave. And this will be areas of low density and pressure. The other word that we use for troughs on this is called rarefaction, not fraction. There's no R in there, okay? It's rarefaction. So in other words, where you see compression, that's going to be a crest, and where you see stretch, that's going to be a trough. Crest, trough. Makes sense? And right here would be like your equilibrium position. So this is exactly what you're seeing. You're squeezing the wave together and it's pulling it apart. It's squeezing it together, pulling it apart. Okay, that's exactly what a longitudinal wave is going to look like, which is what a sound wave is. We can show you that as well during class. Your wave speed equation is going to be velocity equals frequency times wavelength. Velocity equals frequency times wavelength, in which frequency and wavelength are going to be directly related to each other. In other words, one goes up, the other one goes down. So the speed of a wave changes when what two properties are altered? Obviously, it should make sense that it's the medium. But think about some other very obvious factor that is going to change the speed of a wave. Things are going to move faster and slower at different times in the day. Why? Because the temperature is changing. So temperature is also going to have an effect on what the speed of a wave is while traveling through a given medium. Obviously, you don't want both of those variables to change simultaneously. So the next question is, how do waves transfer energy? You guys did have a 1 and a 2 bulletin on your paper. Omit it, okay? All I want you to know on this slide is waves transfer energy by vibration of matter, not transfer of matter. Because if it was transfer of matter, that would mean parting of the Red Sea is what you would end up seeing. Okay, practice D problem here. You have a velocity at 343 meters per second. You have a frequency at 264 hertz. And you are trying to figure out the wavelength. So velocity equals frequency times wavelength. Whereas velocity over frequency is wavelength. Your velocity is 343, your frequency is 264. Plug that into your calculator. You get roughly 1.31. Your final answer, you want 3 sig figs, so 1.31 times 10 to the 0th meters is lambda. That is your final answer. Okay, on your next slide here are your answers to practice problem D. And then I'm also going to state that for the rest of these slides, 11.4, there are no practice problems that go with them, but you still need to watch the video. So there'll be an 11.4 video. It won't be like 11A, 11C, okay? Makes sense? All right, so make sure you guys look at them as well. That is all.